Okay, so I'm going to talk about branching random walks with power law steps. I'll explain what it means. But before that, these are my collaborators, among which Ayan was my PhD student, who is now an assistant professor in IIT Bombay. So first and foremost, the most important slide is to congratulate Deepak once again. And I feel really, really honored to be able to be a part of this conference. I thank the organizers for inviting me, especially because I come from a different community, and we all are really inspired by you, Deepak. So it's great. Thank you. So what I'm going to talk about is branching random walks. So let me explain what it is. But before explaining, let me give you in broad what it means. So roughly speaking, this is a growing collection of particles or organisms, you can say colony of bacteria, which starts from a single particle or a single organism, and then it branches and and spread independently of their positions and the other particles. So this is the rough description. I'll be more precise in the next slide. Now this is the toy model, and we are not going to allow any interaction between the particles. The particles are going to move, but they're not going to interact at all. And they also we'll assume that they can sort of cross each other without colliding. So you can think of so we'll move in a line, the particles will move in a line, but you can think of they're moving in a very thin strip, so they can sort of cross each other without colliding. Now the question, the broad question that we'll try to address is what is the long run configurations of the positions of the particles? And this is, I'll try to at least make it precise what this means in this talk. Now, this model was introduced by Begins in 1976, but since his work was based on these two papers by Hammersley and Kingman, whenever anybody talks about branching random walks, so they always refer to these three papers. Now, what is the dynamics? So let me at least explain that nicely. So basically, you start with one particle at the origin. So this is, we call it the root. This is at time 0. So in my description, at least in this model, time is going to be discrete. Okay. So at time 1, what happens is this particle splits into a random number of particles, and each particle makes a displacement independent of each other and independent of how many particles were born. Okay. So, and the splitting happens according to what is called a progeny distribution. And displacement happens according to a displacement distribution. These are both random variables. And should I do something? And then now you have 3 particles like here. They are in 3 different positions. Now each of these will behave independently of each other and do the same dynamics. So this will go on. And then this will just go on. So that will, this is time 1, then this will form the time 2 particles, then time 3, etc. This will just go on. Now, see from this picture, it's allowed that some particle just dies off. It doesn't split at all. That's also allowed. Okay, so what we see is a branching random walk, but the important thing is that we don't see this entire genealogy, like which particle is coming from which parent, etc. We always, in the end, we only see a snapshot of the whole thing. Okay, so we just see what's say at time 3, we'll just see these particles. We won't see anything else. Now, why is it important? It is important because it is connected to various models in probability theory and statistical physics. So here is a list. I don't want to tell you the connections, etc. But if you want to know about them, you just look at this lecture notes by Zhan Shi. So, okay, so I'll make 2 very simplifying assumptions so that I can present this talk within 20 minutes. So first assumption that I'll make is that for simplicity, I'll assume that each particle in the system branches into 2 particles all the time. So there is no randomness there for the time being. In the end, I'll address what happens if it's random. So in particular, we'll look at what is called binary branching random. Okay? And we're also going to assume that all the displacements are positive. So we know that displacement, the model that I'm at least presenting, all the displacement are IID, which means they're all independent of each other and they have the same distribution. We'll assume that they're all positive and they follow a power law distribution. the power law distribution means that for large x, the displacement is going to be bigger than x with probability some constant times x power minus alpha, where alpha is a positive tail parameter. Okay, so with these two assumptions, what is the question? The question is, how does the system look like in the long run? Again, this is a vague question. So I'll make it a little more precise, still vague, is that how fast does the system of particles grow as time goes to infinity, and what is the scaling limit? That's the question that we want to address. And this was the prediction given by Eric Bonnet and Bernard Derrida in 2021. So they said that the long run configuration of the particles in the system is a decorated Poisson process. Okay, and they also said that it's this long run configuration actually satisfies a symmetry relation called superposability. I'm going to tell you what it is in the end in this particular context. Anyway, so instead of asking these vague questions, let's ask a very precise question. So for example, we know that since we are only considering binary branching, at time n there are 2 power n many particles, and all of them are moving towards the right. So entire dynamics happens on the right side of the real line. Okay. So at time 3, therefore, there are 8 particles. Now we look at the particle which is at the rightmost in time n. Okay. So say that's Rn away from the origin. The question is so this is Rn. How fast does Rn grow as n goes to infinity? And as you can guess, I mean, the particles are spreading. So of course, there will be a growth of the system. The question is at what scale does it grow as n becomes larger and larger? It was proved by Rick Duret that in this context, Rn actually grows like 2 power n over alpha. He didn't just prove it for binary case, he did it for general case, but I'm just presenting his result in the binary case. And he also showed that if you divide Rn by 2 power n over alpha, it converges to a strictly positive random variable. It's basically the Frechet type extreme value random variable, if you know what it is. Now then you can also ask other questions. For example, you can ask what happens to the position of the second rightmost particle. So you basically look at these guys, and then this is the second rightmost particle. It's this much away from the origin. What happens to that in the long run? In particular, does it have a scaling limit like the rightmost one? Also, you can ask about the gap statistic. So if you look at the difference between the rightmost and the second rightmost, that's the first gap statistic. Similarly, this distance is the second gap statistic, and so on. So as n becomes larger and larger, what can you say about the gap statistic? Is there a scaling limit to that as well? And we know that the entire system is sort of growing like 2 power n over alpha. So therefore, the right question to ask would be, I don't know why this is, anyway, it's okay. The right question to ask is basically, I have this, is it possible to remove this thing from here? I'm not so good with Zoom, but yeah. It's not possible?
Click on the chat.
Okay.
And then click on the chat.
Yeah. Remove the chat. Okay. Thank you so much. You're a genius. Thanks. Oh, doesn't help though. Okay. Yeah.
You can't have to control.
Oh, there. Okay. That's fine. So I'll just say what it is. So you just divide these guys by 2 power n over alpha because the entire system is growing like 2 power n over alpha. So you divide and then try to find weak limits of this system. Yeah. Oh, thank you. From there, perhaps. Yeah. Okay. So why can't I move it now? So now question is, how do you tackle these problems? There are lots of problems here, right? The gap statistics, there's order statistics, etc. Now, of course, you can use the brute force method, which I like very much. But then the problem is that this is neither elegant nor efficient. And the main problem would be that every problem you have to attack separately. It's better to develop some technique that can be applied to a large class of problems. And that's what is called the point process technique. And what I want to do in this short talk is this can be thought of as a master key for many locks. And I'll just give a glimpse of this method without going into the technicalities of the entire thing, so that students and postdocs, everyone can use this method if they want to. Okay, so what is this method? So before I say, I just want to just quickly recall what is I call weak convergence or convergence in distribution. So here I'm only going to consider random variables which are discrete with non-negative integer values they will be taking. So, and then I'll have a limit which is also going to be of the same kind of random variables. So non-negative integer value random variable. Here, this notation, weak convergence or convergence in distribution will just mean that probability of un taking a particular non-negative integer, this probability will converge to the probability of u infinity taking that particular integer. Okay, so it just means that in the distribution or the probability mass function of the random variables converge. That's all this means. Okay, so what is this master key that I want to present? So fix an x. Now we know that the entire system is growing like 2 power n over alpha in this special case. So what we do is we look at the point 2 power n over alpha times x. Sort of we stretch the space, using this scaling. Now look at the points. Now I see that how many of my points in the nth generation are to the right of this guy. So here, for example, this is what I call nnx. This is the number of particles at time n that are further than 2 power n over alpha times x, further away from origin. Okay, so you can think of it differently. Since the entire system is growing like 2 power n over alpha, you divide the position of each particles by 2 power n over alpha, and then you look at how many of them are right of x after this scaling. This is another way of looking at it. Okay, so then this is the random variable, and obviously, since the total number of particles in the nth generation is 2 power n, this is clearly a discrete random variable which takes values in this set 0 to 2 power n. Now my question is it possible to find the limit of these guys, the in-distribution limit? So this is the master key. Now, how does that help? Let me just try to tell you how it helps. So if you know this, if you somehow know the limit, somehow able to calculate this limit of these guys, then you can recover the Rig-Duret's result, for example. So here, you divide Rn by 2 power n over alpha. I want to find the scaling limit of this guy for every fixed x. Now, this is same as the rightmost particle is less than or equal to 2 power n over alpha times x, which means there is no particle to the right of this guy, 2 power n over alpha times x. So whatever I call nnx is the number of particles which are further than this guy away from the origin, that should be 0. And that, because I know the limit, should converge to probability of this guy. So therefore, from this calculation, if I know the limit explicitly, then I will be able to compute this limit, and then I'll be able to prove Rig-Duret's theorem. Similarly, you can do the same thing for, why is it the master key? Because you can do the same thing for, say, second rightmost. And this calculation, I'm not going to go into the details, but if you look at the second rightmost particle, that after scaling is less than or equal to x can be written in terms of this limit of these random variables. It's a very easy calculation. Maybe I can quickly go over it. It's just that second rightmost is less than or equal to x after the scaling means this happens. Second rightmost is less than or equal to a point means either of the two things will happen. Either all the points will be to the left of this point, or exactly one would be to the right, all the others will be to the left. That means that either this nnx should be 0 or nnx should be 1. And then in limit, this will just give you the same thing with n replaced by infinity. And therefore, once you know the exact distribution, you'll be able to calculate this. Now, as you can see, this is nothing special about first or second, rightmost particle. You can do the same thing for anything. Kth rightmost particle, and you can, with a bit of more work, you can also look at the joint distribution so that you can also get hold of the gap statistics, etc. Now, let me tell you the final result that we have. So what we have is we have the limit of these guys, and the limit as predicted by Brunet and Derrida has a decorated Poissonian limit. So what it means is that more precisely, this limit. So this looks like a sum of 2 power geometric random variables. And the sum is a random sum, and it's a Poissonian sum. So this 2 power GI is what are called decorations, and this is the Poisson. This PX is the Poisson. So if you don't want to look at the limit, it's enough to know that this is very, very explicit. We know the exact distribution of what it is. And once you know it explicitly, you can go back and you can calculate the limit of the rightmost particle or the second rightmost particle, etc. Okay, So before I go to that, I just want to tell you what is the superposability of the symmetry that the limit satisfies. So suppose A1 and A2 are two real numbers, positive real numbers satisfying this equation. What you do is you run two independent branching random walks, okay, and then you calculate these limits. That we calculated in two of these systems independently. And superposability means the following distributional symmetry. In the first one, if you look at the number of particles that are away from 2 power n times x over a1, and in the second one, if you look at the same thing of x over a2, and then you take the sum, this has the same distribution as the limit n infinity x. So obviously it's a limit, and limit, as we know, satisfies many symmetry. And in this case, it so happens that this is the right symmetry to look at. And this was predicted by Brunet and Derrida. And I should mention that in a case when the displacements are light tailed, were actually proved by the same thing was proved by Thomas Madul. Okay, so the consequence is that you can get back recruited result, and you can prove more results. And I've only stated the result for the second maxima here, second rightmost point. You can do it for any kth rightmost point. And you can also look at the gap statistics. By the way, Gregory here asked this question to Ion in one of the meetings, and we could answer this question. So he asked the question about the gap statistics. Can you find the asymptotics of that? And we could solve that problem from our techniques. And of course, I would like to mention that this binary thing is just a toy example, just to tell you easily. But if you have m offsprings, then the 2 power gi in the limit would be replaced by m power gi. More generally, if you have random branching, then this will be replaced by mu power gi, where mu is the progeny mean, average number of particles in each generation, average number of offsprings in each generation. And displacements, I just assume to be positive for simplicity. They don't have to be positive. And then we have also extended this to various other setups, which are mentioned here. And there are many open problems, and I would say more open problems than what we know. There are more questions that are not we don't know the answers to. For example, how to allow interactions. If two particles, they either kill each other or they coalesce, what will happen? Or also more explicit limit in the light tail case. It's the explicit limit in the light tail case. In the light tail case is not known. And also any statistical inference. For example, how to estimate this parameter alpha in branching random walk. It's a very difficult statistical problem. So I think that's all I would like to say. So thank you very much.